Hello, this is Nicholas with a part 2 of the calculus review from the overwhelming support in part 1. So I decided I'm going to make a second part to feel good about myself. No, not really, not to feel good about myself. To help you guys. Maybe a little bit of that. No, not really. So I decided that this second part will be mainly trigonometry and an introduction to limits, because that is how derivatives and integrals are defined through, and trigonometry is an awful handy tool for those. So I just have kind of written down here the definitions for the 6 basic trig functions. There's a lot more, and you'll learn it. There's hyperbolic trig functions, for example. Anyways, so this is a unit circle here, radius of 1, and I picked a point along a circumference xy. I'm sure you've seen this before. This distance is x, this distance is y, r is 1, and I'm going to call that angle theta. And this is what the 6 trig functions are defined to be right here, and hopefully you can see that sine is the reciprocal of cosecant, cosine is reciprocal secant, tangent is reciprocal cotangent, yada yada yada. And from this picture here, right, you can see that this is a right-angled triangle, because what I've done is I've drawn a line straight up to that point there. So what that means is that by the Pythagorean theorem, x squared plus y squared is equal to 1 squared, which is equal to 1, right? 1 squared is 1. What is x? X is cosine theta, so cosine squared theta plus, and then y is sine squared, or sine, so and then you're squaring it, sine squared theta is equal to 1, and that's probably one of the most fundamental trig identities you're going to know. Now, if you divide this by, if you divide both sides by, let's just start with sine squared theta, then you get that, what? You get 1 plus cotangent squared theta is equal to cosecant squared theta. And if you divide both sides by cosine squared theta, then what you're gonna get is the third Pythagorean identity, which is 1 plus tan squared theta is equal to secant squared theta. And these are going to be very important to know. And sometimes you're going to even have to go in reverse sometimes in calculus. A couple of times, actually. For example, sometimes you might have a 1. You might have to write that as cosine squared theta plus sine squared theta. And that just kind of takes really experience, I guess you could say. Kind of knowing what to do. For example, if I was to ask you to simplify 1 plus sine 2 theta so that it doesn't have a radical in it, then, right, you might be thinking, well, how am I going to do that? Well, you could look at the 1 as sine squared theta, and then sine 2 theta, hopefully you know, as 2 sine theta cosine theta, right, plus cosine squared theta, right, from that 1. Right, but this can be rewritten as sine theta plus cosine theta, quantity squared, which is plus or minus sine theta plus cosine theta. And that's actually one of the integrals I was doing the other day. But so in other words, you have to know your trig identities very well. Now, I mentioned sine 2 theta being 2 sine theta cosine theta. Now, there's a lot of other, oh, I don't know if you can see that all the way. Sine theta plus cosine theta. And that's plus or minus, because you are squaring and then square rooting. So, what was I going? Where was I going with this? Oh, I was going that I mentioned sine 2 theta being 2 sine theta cosine theta. And there's a bunch of other trig, like angle addition, angle subtraction, double angle, half angle, all these other formulas. I'm going to try to provide a way so that you can know all these, because I really don't like using the word memorize with math. I think if you can kind of derive the formulas, you have a better chance at understanding them and therefore memorizing them. So the way that I always think is the simplest with deriving all these different trig formulas that we have is through de Moivre's theorem, or de Moivre's theorem if you're cool. So, well, what is de Moivre's theorem? Hopefully you remember, but kind of the powerhouse behind de Moivre's theorem is the equation e to the I theta is equal to cis theta is equal to cosine theta plus I sine theta. Now traditionally they'll just write e to the I theta equals cosine theta plus I sine theta. And also traditionally they'll just let cis be cosine theta plus I sine theta. So I just wrote it like that. Hopefully this is familiar to you all. And one of the interesting properties is that, right, if you have e to the I theta, also theta has to be in a radians. It has to be in theta has to be in radians. All throughout calculus, you're going to be locked in radians. If you go to degrees, you're going to have to use conversion factors and all these other things. So just kind of remember, when you're in calculus, you're using radians. So if you have e to the I theta to the n, right, by exponent properties, that's just e to the I n theta. So how does that help us? Well, it helps us in a number of ways. For example, if I forgot that sine 2 theta is 2 sine theta cosine theta, what I could do is I could use this property. I could say, well, e to the I theta squared is equal to e to the 2 theta I. And why does this help me? Well, because I have a 2 theta as my input here, so, and I have a sine here, right? So maybe I can, see some sort of connection. So what does this imply? It implies that cosine theta plus I sine theta quantity squared is equal to what? Cosine 2 theta plus I sine 2 theta. And this is good, right? Because you have a sine 2 theta. And over here, we're just going to get sine thetas and cosine thetas and, minus signs and plus signs and all that. But in other words, we can set the, okay, well, let me square this first before I go into that. So we get, sorry if my hand's going to be in the way. So I'm squaring this. We're going to get cosine squared theta, and we're going to get 2 cosine theta I sine theta. So I'm going to write that as plus 2I sine theta cosine theta. Now we're going to have I sine squared theta, or I sine theta squared, which is going to give us I squared sine squared theta. And I squared is -1. So we just have minus sine squared theta is equal to cosine 2 theta plus I sine 2 theta. Now, so an important note is that what we can do is we can equate the real parts with the real parts, right? The real parts with the real part. Hopefully you see this already. And the imaginary parts together, because basically what we're saying is, by the definition of complex numbers, a plus bi is equal to c plus di, if and only if a equals b and c equals d, right? Then they would be the same, right? A plus bi equals a plus bi. So I'm going to equate cosine squared theta minus sine squared theta with cosine 2 theta, and that's actually what it turns out to be. Cosine 2 theta, theta, that's a theta, I swear it is a theta, is equal to cosine squared theta minus sine squared theta. And I'm going to let I sine 2 theta be equal to 2I sine theta cosine theta. And hopefully you're seeing already, I can just get rid of the i's and get that sine 2 theta is 2 sine theta cosine theta. And that's really a pretty nifty way of deriving it. Most other proofs for it are very long. This is the shortest proof I know. Now I'm going to leave this to you all, but if you let theta equal a plus b or a minus b, then you can derive the angle addition and angle subtraction formulas for cosine and sine, if you ever forget them. As far as the double angle formulas are concerned, I got them right here. For the half angle formulas, how do I normally do the half angle formulas? Oh, okay. So, cosine 2 theta is cosine squared theta minus sine squared theta. Now we know from, where is it? This identity, that cosine squared theta plus sine squared theta equals 1. that we can let cosine squared theta be 1 minus sine squared theta. So cosine 2 theta is also equal to 1 minus sine squared theta minus sine squared theta. So that's 1 minus 2 sine squared theta. Or if we were to let this sine squared theta be 1 minus cosine squared theta, we'd have cosine squared theta minus 1 minus cosine squared theta, which is equal to 2 cosine squared theta minus 1. And those are all equivalent forms, by the way. And you'll see probably all three of those written in a calculus textbook or whatever, something like that. So if I wanted to get a half angle formula for sine, say for example, cosine 2 theta, I know as 1 minus 2 sine squared theta. So that implies that cosine theta, right, is equal to 1 minus 2 sine squared theta over 2, right? If that doesn't make sense to you, I could have let theta be x, for example. Let x be 2 theta, then theta is x over 2, right? Okay, so what does that mean? It means, what do I want to do? I'm probably gonna have 1 minus, I'm gonna bring cosine theta over 1 minus cosine theta is equal to positive. I'm gonna add that 2 sine squared theta over 2. I'm going to divide by 2, and that goes away, and then I'm going to take the square root. So that goes away. So sine theta over 2, plus or minus, is plus or minus square root 1 minus cosine theta over 2. And it turns out that cosine theta over 2 is just 1 plus cosine theta over 2, square root, and plus or minus. What else? Oops. What else? Oh, power reducing formulas. These are going to be very, very, very helpful for you, especially in integration. For example, cosine squared theta. Let's say I have cosine squared theta. My question to you is, how could I write that so that the largest exponent is 1? Well, where did I write it? I wrote it here, right? Cosine 2 theta is equal to 2 cosine squared theta minus 1. So what I'm going to do is I'm just going to isolate cosine squared theta. So that's equal to 1 plus cosine 2 theta. Oh, there's over 2. Right? I added 1 and then divided by 2. And see, now the largest exponent is 1. Now you're probably thinking, well, why the heck is that helpful? Well, my best answer for you is you'll see. And probably with this equation, you're thinking, well, how did you get that? Well, my best answer for you, again, is you'll see. I would love to show you the proof, but it kind of requires Taylor and Maclaurin polynomials, which I don't think anyone really knows as of now. Okay, so I've kind of gone over that. Oh, another thing I saw in the book that will be important later when you are doing trigonometric substitution in integration is, so for example, I know one of the problems was cosine, or something like this, of arc sine of, I don't know, 3/5, right? And they want you to simplify that. Oops. They want you to simplify that. So, okay, you're probably thinking to yourself, well, what the heck? But so, let me ask you a different question. What is sine of arc sine of 3/5? Okay, I know this isn't answering the question, but you'll see. Oh, oopsies. So what is sine of arc sine of 3/5? Well, okay, it's 3/5. Now, why is it 3/5? Because arc sine of 3/5, right? You're plugging in a number and you're getting an angle, right? And then you're taking the sine of that angle that you used to get 3/5, and you're going to get 3/5, right? You see they're inverses of each other. Sine and arc sine are inverses of each other. And by the property of inverse functions, right? If you have f of f inverse of x, that's equal to x always. If you have and any function is invertible, so that property is true always. So you get 3/5. Now, what am I going to do? I'm going to let arc sine of 3/5 be equal to theta. Okay. Now I know that the cosine of theta is equal to 3, the sine of theta is equal to 3/5. So this is theta. we got a 3, we got a 5, so this has to be a 4. So this whole thing, cosine of arcsine of 3/5 is equal to, right? So we're taking the cosine of this angle. That's 4/5. 4/5. That's it. I know there was something like that. Oh, this was one that Mr. Mack was doing today in class, and I think probably got a good bit of people confused. He, you know, he let phi be an angle such that I think cosine phi equals 1/√5. And we were trying to solve, right, one of the answers was I think arctan of 4/3, and we were trying to solve for that trig function, right? One of our solutions was pi, and then the other one was arctan of 4/3, I believe. I don't have the exact question with me because I don't have my book, but the reason, well, why did he divide by √5, right? So basically what this comes down to is what's known as the harmonic, and you can kind of put the word angle in if you want. Harmonic angle addition theorem. Very helpful theorem to know, just kind of to have in your bag of tricks, I guess. What it says is that if you've got constants a and b, a cosine theta, or a, because I'm going to use theta later, a cosine x plus b sine x is equal to, this is a different constant, a, cosine of x minus theta, where a is equal to the square root of a squared plus b squared, and theta is equal to the arctangent of b over a. Now, probably thinking, well, what the heck, where did you get that from? So I'm going to prove it to you because I like proofs. A cosine x plus b sine x is equal to a times, now we have cosine x minus theta. This is one of those trig identities you should know. That's cosine x cosine theta plus sine x sine theta. So we get, that implies that that's equal to a cosine x plus b sine x, which is equal to a cosine theta cosine x plus a sine theta sine x. Now look at these coefficients with me. We have an a and then a cosine x. And here we have a capital A cosine theta and then a cosine x. We have a b and a capital A sine theta and a sine x. Now this a is the coefficient in this cosine x, and this capital A cosine theta is the coefficient of this cosine x. This b is the coefficient of the sine x, and this a sine theta is the coefficient of the sine x. So what does this mean? It means that little a is equal to big A cosine theta, and b is equal to a sine theta. So what, right? What am I gonna do with that? I'm gonna square both of these, so we get, I'm gonna square a, I'm gonna square b, and I'm gonna add them together, right, because of this. I'm gonna get a squared plus b squared is equal to what? A squared cosine squared theta plus a squared sine squared theta, which is equal to a squared cosine squared theta plus sine squared theta, which is equal to a squared, because this is 1. So capital A squared is equal to little a squared plus b squared, so like I said, a is equal to the square root of a squared plus b squared. Pretty cool. And then what is theta, right? Okay, so we know that we have these two conditions. A is equal to a cosine theta, b is equal to a sine theta. Now if I was to take b over a, what I would be taking is, what? I'd be taking a sine theta over a cosine theta. The a's go away. You get that b over a is equal to tan theta. So it follows that arctan of b over a is equal to theta. That is a very cool theorem, and that's why he divided by root 5, right? There was a 2 in front of your cosine x, and there was a 1, right? It was just sine x, but that's really 1. And so he took that, and basically what he did is he completed the square, so to say. Now, he could have used this theorem as well. And also, another interesting thing that I should probably mention, it will also come up as an integration technique, but this substitution can also convert any rational polynomial or any sort of function involving sines and cosines into a rational polynomial function. And basically the substitution that you can make is you can let t be equal to tan x over 2. And this was proved by what's his name? Weierstrass or something. And you're thinking, well, why the heck would I do that? And I don't have a proof for you. But this does turn out to work. So you're probably thinking, well, you were talking about sines and cosines, but I substituted in tangent. Well, I know. So we have to write sine and cosine in terms of t. So this angle here is x over 2. So this is t, this is 1 because tangent, right? It's really t over 1. So this is the square root of t squared plus 1. So sine of x is equal to 2 sine x over 2 cosine x over 2. So that's 2 times t over square root of t squared plus 1 times cosine, which is 1 over square root of t squared plus 1. So you get 2t over 1 plus t squared is sine x. And cosine x, what did I say that to be? Cosine squared x minus sine squared x. So that's, cosine 2 theta is that. So cosine theta is cosine squared theta over 2 minus sine squared theta over 2. So we get, we get t over square root 1 plus t squared, minus, wait, have I done this wrong? Yeah, this should be a 1. This should be a t. This is sine, yeah. 1 plus t squared. So we get, that's equal to 1 minus t squared, yeah, over 1 plus t squared, right? Because square root squared, same, and then you just have the same denominator. So, yeah, you can just, that's how you would write them, and you get an answer. For example, sine x plus cosine x is equal to 1/3. So I'm gonna let t be equal to tan x over 2. So what does that give us? So we derive right here, sine x is 2t over 1 plus t squared, so we get 2t for 1 plus t squared, plus we have 1 minus t squared over 1 plus t squared is equal to 1/3. So, where am I? I want you guys to see how it works, but this tripod's in the way. Okay. So we get negative t squared plus 2t plus 1 over 1 plus t squared is equal to 1/3. T squared minus, what am I gonna do here? What am I going to do? I don't really like this negative here. in front of the t squared. So I'm going to pull that out. Negative of t squared plus 2t. I think I'm going to complete this square. So I'm going to add 1. Oh, yeah, so I'm going to add 1. Okay, that's really a negative 1. And we had a 1 there, so I need to add 2. Right, because we had a positive 1. And then this is, I'm adding positive 1, but the negative out here makes it a negative, and then we add 2 to make it 1 over 1 plus t squared. It's equal to a third. Now this really is kind of ugly, but it does work in absolutely every case, so it's kind of good, I guess. Anyway, so we get that this is equal to negative of t plus 1 squared plus, maybe I'm going to write this as the square root of 2 squared for 1 plus t squared, which is equal to a third. Oh, yeah, this isn't really leading anywhere all that nice. You could just kind of, if I were you at this particular point, I would just kind of, I would just kind of really look at a graphing tool or something like that at this particular point. Okay. What have I not done? Oh, someone asked me to do graphing trig functions, so let me do that. Okay. Boss, this is for you, so you better watch up to here, all right? Okay. So, graphing trig functions. So, the most general form, say we're dealing with sine, for example. The most general form a trig function can be in is f of x is equal to a cosine of b times wait, I've butchered this a little bit. Oopsie. Graphing isn't really something I'll enjoy that much, so I don't really look at the forms as much. Okie dokie. Just give me 1 second. Okay. Alright, sorry, okay, yeah, I was, oh, I should write next. I was thinking of t with the other one. X minus c plus d. Okay, so that probably needs a little unpacking. So what is A? A is your amplitude. Your amplitude. In other words, how far you go from kind of your middle resting point to the top or to the bottom. It's given by the absolute value of A. Your period, in other words, how long it takes to complete a cycle, is given by, in this particular case, 2 pi over b, because the traditional period of cosine is 2 pi, but then you're multiplying by a factor of b within the input, so you have to divide by that in the output. Your phase shift, is going to be, in this particular case, c units right. Not left, right. Because the way you can think about this is, so if this was just bx plus d at the end, and say you plugged in 0, right? Now it's x minus c. You have to go over c to the right in order to get 0, right? You have to go over c just to get 0, and then everything after that you have to go over c more, right? So it's c to the right. And your phase shift, right, that's just moving left and right. That's just the graph moving left and right. And then your vertical shift, which I'm sure you've guessed, is d. So as an example, that's what I was just looking at, because Can't come up with a real good example off the top of my head. So if we have f of x is equal to negative 5 halves tangent of 4x minus 3 pi minus 4, because I used 4. So what is our amplitude? Our amplitude is not negative 5 halves, it's 5 halves. It's the absolute value. Amplitude can never be negative. Your period, what do you think your period is? Well, basically the idea is that you can rewrite this as negative 5 over 2 tangent of 4 times x minus 3 pi over 4 minus 4. And so what does that tell you? It tells you that your period, right? In other words, this is what you're multiplying your input by, and then this is your phase shift here. So you, basically what it comes down to is that your period, right, is the traditional period of tangent, which is pi, not 2 pi, over that 4. Pi over 4 is your period. Your phase shift is 3 pi over 4. Right, you have to go over 3 pi over 4 for you to get to 0, and then another more, you know, if you go more 3 pi over 4 to actually continue on with the graph, so to say. And then it's shifted 4 down because of that negative 4 there. You can graph that if you want. I'm not graphing that. Okie dokie. I think that pretty much takes care of trig. So, and I'm 30 minutes in, so that's pretty good. I am going to start then with dealing with limits, okay? And I'm probably gonna just start this on the back page. I don't know why I'm drawing a line in though. I'm starting on the back page. So, what is a limit? Well, probably the idea of a limit is relatively intuitive to you. The way it's actually airtightly defined, so to say, is not quite as intuitive. That's called the epsilon delta definition of the derivative. And you'll learn about that a little later. Not very far down the road, pretty close. So a limit. Basically, the idea is you're looking at a function and you're getting closer and closer to a specified value, right? And you're looking what the output of the function gives based on you approaching some input value within that function. So let me give an example. This is just very, very basic example. Y is equal to x plus 2. Right? It's a line, y-intercept of 2, negative 2 here at 0, like this, right? Now if I was to ask you, what is the limit as x approaches negative 2? Oh, and by the way, that's how we denote it, lim, as x approaches negative 2, of y, which is really the limit as x approaches negative 2 of x plus 2, well, you would just say, well, 0, right? I mean, look, I should have drawn that a little bigger. I'm going to do that. This is negative 2. There's your graph, right? As you approach negative 2, right, from here and from here, right, what are your values closing in on? They're closing in on 0, right? Say if you plug in 0.00000000001 for x, right, you get basically, or I'm sorry, we're approaching negative 2. If you plug in negative 1.99999999999 for x, right, you get basically negative 2 plus 2, which is basically 0. Of course, you could just plug in negative 2, right? If the function is defined at that point you're approaching, then just plug it in and you've got it. So, of course, they're not going to be this nice to you. They're going to be a lot meaner to you. And always, but realize that people often forget that, of course, you can still take the limit where the function is ordinarily defined, right? Sometimes books will do that at an ordinarily defined point, and people will be like, well, what? But I mean, it's, you know, so this is known as direct substitution, where you just plug in your limiting value into your x, and you get your answer, right? You're approaching -2, and your y value that you're approaching is 0. Okay, so what next? That was what's known as a two-sided limit. And what do I mean by two-sided? I mean that we approach both -2 from the right and from the left. Okay? We approach from the right and we approach from the left. So what we can do is sometimes if we have, you know, kind of wacky functions, if we've got like, I don't know, maybe this is, say, 1, and this is 1, and then maybe it jumps over to here, right, at 2, and then maybe it does that, and maybe this does that, you know, just crazy functions. This is normally what they'll give you in your book, just to be mean to you. Okay. So if we're to deal with this is a situation where they'll most likely ask you about one-sided limits. And so what do they mean by one-sided? Well, hopefully you could guess that you're just taking the limit as you approach from some certain direction, not from both directions. So for example, if I was to ask you just generically, the limit as, and we're going to call this function f of x, right? As x approaches 1 of f of x, what would you answer to me? You're probably either going to say 1 or 2, right? Because as you approach from the left, right, you approach 1. As you approach 1 from the right, you approach 2. Oh, and this brings up a very important point. A function does not need to be defined or continuous or at that point at which you are approaching in your limit in order for the limit to exist, right? We don't care what the actual value of the function is at that point. We only care what it approaches at that point. For example, if I had drawn here this -2, but said there was a removable discontinuity here at -2, then the limit as x approaches -2 of this x plus 2, right? It's still 0. You get closer and closer to -2, you still get to 0, but at 0 it's not defined, but that doesn't matter. We're not asking for f of -2. We're asking for the limit as x approaches -2 of f of x. They're two different things. A function does not need to be defined where you're taking the limit at. It's a very important thing to know. Okay, so if I were to just ask generically the limit as x approaches 1 of f of x, which is this function here, if you approach it from the left, you get 1, right? You approach from the left, right? You're coming in, right? And now you get to 1. But if you were to approach from the right, you're coming in, and you're getting closer to 2, right? Coming in at 2. So, well, which is it, right? Is it either 1 or is it 2? Well, it's neither in this particular instance, since the one-sided limits are not the same. In other words, you approach 1 from both sides and you get two different answers. So this two-sided limit does not exist. DNE does not exist. Yep. Now, of course, if we're to talk about a one-sided limit, for example, limit as x approaches 1 minus, okay, and this is important, this does not mean as x approaches -1 or 1 to the -1 or whatever. It means this minus here means it literally will translate to from the left. That's literally what it means, okay? So don't make that mistake. So as we approach 1 from the left, right? From the left, we get 1, right? We're approaching, and we get 1. And since the function is defined here, that also works out nice for us. But that doesn't matter if it's defined there, right? It does not matter. You can still take the limit. The function does not need to be defined at the point you're taking the limit at, though, okay? It's very important, you need to know. So limit as x approaches 1 from the left of f of x is equal to 1. Now if I was to ask for the limit as x approaches 1 from the right, that's what the plus sign means, from the right of f of x, what would you answer? Well, you're approaching. Looks like you're closing in on 2, right? And that is indeed what the answer is. So you see here how, since these one-sided limits are different, right? Since these are different, the two-sided limit does not exist. In order for the two-sided limit to exist, the one-sided limits have to both be the exact same value. Okay. Now let's kind of just talk a little bit about evaluating certain limits. Okay. The idea with the limit is often they'll ask you a limit at a point of where something wacky's going on, at a point of discontinuity, at a as you're approaching a vertical asymptote, as you're approaching some sort of jump, or something like that. So this is a simple example. Let's say if I was to ask the limit as x approaches 2 of, say, x squared minus 4 over x minus 2. Okay, well, if you plug in 2, right, you get 2 squared 4 minus 4 is 0 over 2 minus 2, which is 0. So you get 0 over 0. And I know for sure I talked about in my last video that 0 over 0 is not 0. It is an indeterminate form. You cannot determine an answer. How many times can you subtract 0 from 0? Well, as many or as little times as you want, right? So the idea is that you want to remove the factor that is causing your discontinuity. That's what I mean by that. Well, this is equal to the limit as x approaches 2 of x plus 2 for x minus 2 over x minus 2. And now notice, right, since we don't actually care what f of 2 is if f of x is defined as x squared minus 4 over x minus 2. We don't care what f of 2 is, we only care what it approaches. So we can just do this. Gone, right? Doesn't matter. And this factor of x minus 2, this is what's causing us to have a 0 over 0 indeterminate situation, right? You get 0 times some number, which is 0 over this 0 here. But when we remove that, we just have the limit as x approaches 2 of x plus 2, which is 4. Ta-da! So, the moral of the story is that you want to get rid of your factors that are causing you to have an indeterminate form. And so for some indeterminate forms that you are gonna just need to know in calculus, I mean, you just can't get away without knowing these. 0 over 0, this is probably 0 over 0, infinity over infinity. These are probably the two most common ones when dealing with limits, because later you'll realize that you can use a rule known as L'Hopital's rule to evaluate the limits in this form. Infinity minus infinity. This is not 0, by the way. This is not 0. I'll probably show that real quick. 1 to the infinity. Infinity to the 0, right? Because that's really infinity to the 1 over infinity to the 1, which is infinity over infinity. 1, 2, 3, 4, 5. It's worth noting that 0 to the infinity is not indeterminate. It is 0. That's all the ones that I can remember off the top of my head. Those are really the most common ones in this order, really. So I'm just going to kind of show real quick why infinity minus infinity is indeterminate. So let's say let's just say we think it's 0, right? For the sake of just, let's say, well, it's the same quantity, right? So we're subtracting it. Well, it's got to be 0, right? Okay. So now what I'm going to do is I'm going to add 1 to both sides. Infinity minus infinity plus 1 is equal to 1. Now, what is infinity plus 1? Well, it's approximately Bill Gates' wealth plus $1, which is still infinity. No, in other words, you add 1 to infinity, you still have infinity. So you have infinity minus infinity is equal to 1. But we just said infinity minus infinity is equal to 0. that means that 1 is equal to 0. But 1 is obviously not equal to 0. So infinity minus infinity is indeterminate. Okay. What is kind of a... Oh, another thing I probably should note to you guys is that dealing with limits as they approach infinity, since I guess I'm kind of talking about infinity, is actually kind of nice. So let's say we have the limit as x approaches infinity of, say, 3x squared minus, I don't know, x plus 4 over 7x squared minus, I don't know, 2x plus 3. You're thinking, well, what the heck? How do I remove this, you know, what do I do here? Well, basically what happens is, so as x approaches infinity, what happens is that these terms here kind of become the dominating terms, in the sense that these terms approach infinity much, much, much quicker than, say, this term, and especially more than this constant, right? This constant, as you approach infinity, you can just ignore your constants, right? You just get rid of them, really. As you approach infinity, they just become insignificant. But since this is square, this approaches infinity much, much, much quicker than these two terms here. And so you can kind of do the same thing that you did with the constant. You can just get rid of them, because, again, these are really what become your limiting terms, so to say, as you approach infinity. These are what control how quickly you approach infinity. These just kind of become insignificant after a while for some really arbitrarily big numbers. So basically what happens is that this original limit is equal to the limit as x approaches infinity of 3x squared over 7x squared. Get rid of the x's, 3/7. Look at that. And so maybe you might think, well, wait, this is what I did to determine horizontal asymptotes in Algebra 2. Well, this is exactly why you did what you did. This is why you took the ratio of the coefficients, because a horizontal asymptote means, you know, as you plug in bigger and bigger and bigger in x's, what does your y value approach? Well, if the degrees are the same, then, like I said, these terms just go away. They're insignificant as you approach infinity. So what happens is your horizontal asymptote becomes the ratio of your leading coefficients through limits. That's why that is what it is. Okay, enough of that. What's another cool type of limit form? Oh, I should probably talk about... Let's do this one, just as kind of an example. The limit... Oh, and then I needed to talk about the definition of the derivative. The limit as x approaches... I don't know. Limit as x approaches... Oh, yeah, so let's just do that. Limit as x approaches infinity of cosine x. Well, what is that, right? What happens is, right, you have a graph and it's going like... Right, it doesn't look... It's obviously... It's fixed. Well, it's fixed between -1 and 1 under the reals. Under the complexes, you can actually get it as big or as small as you want, because... I'll write it just for the heck of it, if you're actually watching this. You can actually get it as big as you want, because cosine of IB is equal to the hyperbolic cosine of B. And that is unbounded. Okay, anyway, enough of that. Under the reals, the range of cosine is from -1 to 1. Okay, so what is this limit? Well, as you approach infinity, right, you go up and down, you go up, you go down, you go up, you go down, you go up, you go down, right? It doesn't look like it's approaching any fixed value, right? You keep oscillating, and that ends up being the case, right? This limit does not exist. It just keeps oscillating back and forth, back and forth. So basically, when you just kind of have limits of trig functions, sometimes what'll happen is that you'll just kind of get answers that do not exist. Okay. I'm probably not gonna talk about too much more. I'm kind of looking up some good examples of limits. In the meantime, I heard that some of you guys were a little confused on the definition of the derivative. And this is very crucial to know. Why is it crucial to know? Well, because you need to know the limit in order to know the derivative, and you need to know the derivative in order to know the integral, and you need to know the integral in order to know the series. It all builds on each other, really. So let's talk about that. So say you got a function f of x, right? Say this is your point x, and say this is a x plus h. Then this right here is f of x. This right here is f of x plus h. Okay. Now the question is, I want to know the slope of this curved function, this nonlinear function, at any particular point x. Well, how can I do that, right? The slope is changing at every instant in time, right? It's not constant like some sort of linear equation where the slope is, the same number throughout. This slope is constantly changing, right? It's growing in this particular case. So what we do is we say that, well, the slope of this graph at any particular instant is defined as the slope of the line tangent to the graph at that particular instant, okay? So if we want to find the slope, of this graph here at x, we would want to find the slope of the line. Oh, that's a horrible tangent line. Wait, that's horrible. What time is that? Oh, okay. I want to find the slope of the line tangent to the graph at x. That's absolutely horrible. And of course, just what? Oh, realize that if I wasn't so bad of a drawer, that tangent is 1 point. It intersects the graph at 1 point. And what we have now, if we were to connect these 2 points, is a secant line, a line that intersects the graph at 2 points. Now, why do we even bother with this whole 2-point business? Why don't we just, have a point here and just draw the tangent line, right? Why even bother with the 2 points? Well, the reason why we bother with the 2 points is because, let me draw the function again. If I just picked any old point and drew a tangent line through it, well, there are infinitely many tangent lines I can draw through this particular point. Oh, imagine that's hitting the point. I could draw this, I could draw this, draw this, I could make a star, I could make an octagon, no. But the point of the matter is that one of Euclid's postulates in geometry says that 2 points determine a line. So if you only have 1 point, you can draw infinitely many lines through that point. That's just one of Euclid's one of Euclid's 5 basic postulates in his book, The Elements. So the reason why we have these 2 points is so that we can determine a line. And then what we do is that we let these 2 lines, in other words, we let h become 0, right? So that this point slides to this x point here, right? It slides to this x point here. And this x value just slides over to here, right? Because h is going to become arbitrarily close to 0. So we have these 2 points approaching each other, and as these 2 points approach each other, this secant line that intersects at 2 points, right, at 2 points, becomes roughly a tangent line that only intersects at 1 point. And that's why we have the whole 2 points to begin with. Now, the slope of the secant line, that's what this m means. It's slope, and that's what the secant, and then it's a line, is equal to y2 minus y1 over x2 minus x1. F of x plus h minus f of x over x plus h minus x. Now obviously those x's go away. Now, what we're saying is we're letting h get arbitrarily close to 0. In other words, we're taking the limit as h goes to 0 of this function, right? And then what that's doing is it's letting the secant line approach a tangent line, which will give us the slope of the graph at that instant, okay? And that's why we have 2 points, and that's why we let them close in on each other and let them become 1 point. Well, they don't actually become 1 point because, like I said, the limit need not be defined at the point you're approaching. So, basically, we have the limit as h goes to 0 of f of x plus h minus f of x over h. And we define this to be the derivative of your function f of x at x. That is the definition of the derivative. It's very, very important to know. Very, 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 very important to know. So hopefully that made sense. The derivative, basically, it can be interpreted as the slope of a line tangent to a curve at a given point. And so if we were to plug in 2 in for f prime of x, and that's how we write the derivative. We can write f prime of x. That's how we signify that. That's the derivative of f of x, f prime of x. There's also another way, but we'll get to that later. So now what? What was I gonna do next? I was just gonna do something next. Oh yeah, so if you were to plug in x equals 2, for example, and say this limit here evaluates to 12, then what that means is the slope of the line tangent to this curve f of x at x equals 2 is 12, okay? And that's one way you can interpret the derivative. There's several other ways, by the way. For example, in the physics we're taking now, when we have these oscillatory motion sinusoidal curve graphs, and we have a displacement versus time graph, the derivative of the function that gives you your displacement versus time graph represents the velocity versus time graph. The derivative of the function that defines the velocity versus time graph gives you the acceleration versus time graph. So that's another way to interpret derivatives. Okay. I may as well, since I have this definition. One other thing to mention, that there's also an alternate definition of the derivative. It can also be defined as the limit as x approaches a of f of x minus f of a over x minus a. And hopefully you can kind of see that these two are saying the same thing. It's basically, you have the slope formula, right? And then you're picking 2 points and you're letting one get closer and closer and closer to that original point. And so basically what you're doing is you're just kind of limiting that 1 point into the other one, and eventually they look almost exactly like one. So again, you have a secant line and it approaches a tangent line. Okay, that's the alternate definition of the derivative. And since I have this definition of the derivative established, I may as well just evaluate a derivative using the limit definition of a derivative. Of course, there would be much more sophisticated ways, I guess you could say, of evaluating derivatives, which we'll get into. But for now, let's say you have f of x is equal to x squared plus 2. And you want to find the derivative of f of x. In other words, you want to find a function derived from f of x that gives you the slope of a line tangent to the curve at any particular x value along x squared plus 2. Okay, so now this is the limit as h goes to 0 of f of x plus h. Well, what is f of x plus h? It's, you let x be x plus h, so you get x plus h, quantity squared plus 2, minus x squared plus 2. And right, that's in parentheses, over h. That's equal to the limit as h goes to 0 of x squared plus 2xh plus h squared plus 2 minus x squared minus 2. That goes away, that goes away, that goes away, that goes away. Oh, and it's over h still, which is equal to the limit as h goes to 0 of h times 2x plus h over h. And now notice, this, like I was mentioning above, this factor of h here is what's causing your limit to be in the form 0 over 0 when you directly substitute. So it'd be very nice when we just cancel it out, right? Now you get the limit as x approaches 0, 2x plus h, which is equal to 2x. So this 2x is a function derived from this original function that gives you the slope of the line tangent to a particular value x along the curve x squared plus 2. That's what this means, to be the derivative of f of x is equal to x squared plus 2. Okay, I will talk about one, so sometimes I know in the textbook they gave you a limit kind of like limit as h goes to 0 of, say, h plus 6 squared minus 36 over h. Now, hopefully you can see, hopefully you can see that this is awfully similar looking to this, which is this, okay? Right, we can write 36 as 6 squared, okay? So basically what's going on here, right? We're gonna, if we're trying to find a function f of x, right, this looks like the definition of the derivative. We're gonna try to find a function f of x that when we use the definition of the derivative will give us this, okay? So this will be f prime of 6, where f of x is equal to x squared. Okay, now, oh wait, x squared? Is that x squared? Oh, let's see. Okay. Yeah, I believe so. So you could use the definition of the derivative, or you could algebraically just kind of go about and say that's equal to h squared plus 12h plus 36 minus 36 over h. I think this is a little easier. So I'm just going to stick with this. It's equal to the limit. So h goes to 0 of h times h plus 12 over h. That goes away, and we get 12, because h goes to 0. So you just have this 12. Okay. Oh. Okay. Yeah. Oh, yeah, I was right with x squared, because like I did here, the derivative of x squared is equal to 2x, and you can see that we plugged in 6 in for here, so 2 times 6 would give you 12. It's another way to do it. Anyway, I'm going to show you kind of another common type of limit. And basically what this technique is, it's kind of a common type of limit that they'll give you. Basically, the technique is called rationalizing the numerator. So let's say we have the limit as x approaches -3 of the square root of 2x plus 22, and this is under the square root, minus your 4 over x plus 3. What I'm going to do is I'm going to rationalize the numerator. I'm going to multiply by 2x plus 22, this is under the square root, plus 4 over the square root of 2x plus 22 plus 4. That gives me the limit as x approaches -3. So this is really a difference of squares. So basically we can just take this squared and this squared. So 2x plus 22 squared is just 2x plus 22. We have minus 4 times 4 is minus 16 over x plus 3 times square root 2x plus 22 plus 4. 22 minus 16 gives you what? Oh gosh, gives you 6. 2x, so you have 2x plus 6. 2x plus 6, which is really 2 times x plus 3. 2 times x plus 3 over x plus 3. And again, notice that the x plus 3 was what was causing the whole, oh, this is limit, as x approaches negative 3. This x plus 3 is what was causing our limit to be in the form 0 over 0. Go away. So now we get the limit as x approaches negative 3, 2 over square root of 2x plus 22 plus 4. Now, yeah, now we can just directly substitute into this limit, right? We get 2 over minus 3 times 2. It's negative 6 plus 22. Oh gosh. Plus 6. 0. Oh my goodness. 16. Yeah, you should get negative 6 plus 22. That's 16. Yeah, that's 16. So square root 16 plus 4, which is equal to 2 plus 4 over 4, which is equal to 8. Or 2 plus 4, 2 over 4 plus 4, which is equal to 2 over 8, which is equal to a fourth. The answer is a fourth for that. That technique was known as rationalizing the numerator. You go see it a lot. It's a pretty standard type of limit, really. One more thing that I will probably mention and then probably be done, because I need to get some sleep at some particular point. Let's say I was to ask you the limit as z approaches 4 of the square root of z minus 2 over z minus 4. Okay, now what many people might not realize is, I'm sure many of y'all know that, for example, a squared minus b squared is equal to a plus b times a minus b. But this right here can actually be factored as the difference of squares. If you think of this, okay, let me just write it out. Limit z approaches 4, square root z minus 2 over, now z minus 4 can actually be written as the square root of z plus 2 times the square root of z minus 2. If you don't believe me, FOIL it out for yourself and see. Now, again, this factor is what is what's causing our limit to be in the form 0 over 0, so bye-bye, it's gone. Get the limit as, oh gosh, I'm writing all slanted. Limit as z approaches 4 of 1 over root z plus 2, which is equal to 1 over 2 plus 2, which is equal to a fourth. Look at that, the same answer. That's pretty crazy. Okay. Wow, I've been recording for an hour and 10 minutes. Time flies when you're having fun. Okay. I just want to do one more just to show you something else real quick. And this will be it. I swear. Okay. The limit as x approaches 1, if I remember this right, of x squared plus 1 over x. Minus 1. Yeah. X squared minus 1. right, what you can do actually is factor out the biggest term under this radical. And this is actually a technique that is helpful in integration as well. Oh, wait. Well, if you just... what do I want to do? I don't want to make this an x. Maybe -1. That way it's actually indeterminate still. No, but then I'll make it an x. Okay. This is the limit. X approaches 1 of this x squared times 1 minus 1 over x squared. Oh, I wanted to make it infinity. That's what I wanted to do. The limit as x approaches infinity. Okay. So we get the limit as x approaches infinity. X squared minus 1 over x. Okay. Over x. Which is equal to limit as x approaches infinity. Okay, now. Notice here that as x approaches infinity, this is going to be positive. This whole thing here is going to be positive. You have x squared minus 1. As this approaches infinity, right, this just becomes positive. So normally when you take a square root, when you take the square root of x squared, you get plus or minus x. But in this particular case, since all we're dealing with is a function that is positive, at least where we're dealing with in the limit, what we can do is just make it an x. We don't have to include absolute value of x or anything, since we're dealing with positive, with a positive function, where we're concerned with in the limit. So this is x times the square root of 1 minus 1 over x squared all over x. And again, this is what's causing us to have an indeterminate form of infinity over infinity. And the idea is that, right, if we, the idea basically in essence is that the limit as x approaches infinity of 1 over x is equal to 0, right? 1 over a really, really big number is 0, basically. But the limit as x approaches infinity of, say, x, well, that's infinity, right? So the idea is that this is much easier to deal with than this. So again, look at the limit as x approaches infinity, the square root of 1 minus 1 over x squared, which is equal to the square root of 1 minus 1 over infinity, which is minus 0, which is equal to 1. And I'm going to finish it at 1. I'm going to finish my answer at 1. Because I think 1's a nice number, and I'm tired. This has gone really long. Look at this. This and this. I didn't use that space there. Yeah, if you have any questions, then I love to answer questions. Well, you'll probably be getting into next, after you deal with derivatives, is a rule which is known as L'Hopital's rule. That basically says that you can take the derivative of the numerator and the denominator of a rational function that you're taking the limit of, if it's indeterminate form via direct substitution. And when you take the derivative of the numerator and denominator of that, you get an equivalent limit. And that's a very powerful rule. So, on that note, I'm probably gonna just call it quits for now. And I want to see the same positivity that I saw in the last video. So, like, I want to see, you know, it would be nice if I could get over 100 views. That would be pretty cool. And maybe, like, I don't know, like 15 likes or something, because an hour and 15 minutes is quite a long time. And I was at Mathnasium before this, working for about 5 hours, so I've done a lot of math today. And then when I got home, I had to take my physics notes. So I've pretty much done math the entire day today. But that's cool. I like it. Anyway, I am going to go now, so we're done.